All right. Hello, everyone. So let me present to you today determining infrastructure resilience to geohazards by satellite and AI. My name is Skevi Perdikou. I'm the CEO of Geofem. And let me introduce the company first before I start with the technical presentation. So Geofem is a satellite remote sensing company with specialization in the infrastructure asset monitoring. So we do that by monitoring infrastructure and ground movements in the areas of interest, but also by providing early warning systems and alerts before they become serious. And also we have developed our own algorithms for assessing the susceptibility to geohazards such as landslides and expansive clays. As a company, we specialize not only in satellite remote sensing, but what is quite unique about us is our geotechnical expertise as well. And the importance of that is in the interpretation and assessment of the outputs and also providing recommendations. So let me share what I will be presenting today. I will talk about some of the innovation we have been developing as a company, which is a soil moisture algorithm via the use of satellite technology, displacement monitoring applications, and also how we use AI and machine learning for infrastructure susceptibility to geohazards. Some of these innovations are the result of our partnership with the European Space Agency, where we work closely and we have several contracts with them, which allow us to develop some of this work. So what is the problem? We're talking about geohazards. The problem is that the geohazards can occur anywhere. And when we talk about transportation networks, railroads, or even urban areas, it's impossible to, it's very difficult to check, especially thousands and thousands of kilometers of these transportation networks. Another problem is that the maintenance is most of the time reactive rather than proactive, which means higher budgets. And also climate change resilience is low. So what I will be talking about today is the use of satellite technology for reducing maintenance costs, and we are proposing this by using space technology to identify problematic areas early on, and in that way we can be more proactive rather than reactive. In this way we can increase utilization of the network, and also by identifying the problematic locations, you can more efficiently allocate your resources for maintenance. Let's talk a little bit about the satellite basics. So here we have our geostationary orbit satellites that maybe most people are more familiar with, and as the word says, geostationary, they remain stationary compared to the rotating Earth. And these satellites are used to monitor development of specific events around the Earth. We also have the SAR satellites that I will be talking mostly about today. So these satellites travel from the North Pole to the South Pole to the North Pole. So if you consider this orbit of the satellites with the rotation of the Earth, then you can see that you can have global coverage with this data. Another also information is that we consider ascending when we receive data while the satellite is traveling between the South Pole and the North Pole, and descending when the data is obtained from the North Pole to the South Pole. Now, what is SAR or INSAR? I'm sure most of you or a lot of you have heard this word, but what it stands for is synthetic aperture radar. So we start with R, which is radar. So radars are different. They operate in a different way to optical satellites. So they do not rely on sunlight to operate. Instead, they transmit electromagnetic radiation, and they measure the reflections back to the satellites. They have the characteristic of penetrating the clouds because they operate in microwaves and radio wave portion of the electromagnetic spectrum. And that's very important because it means we can have data under any weather condition. also operate day and night. A stands for aperture, which just means antenna, and S stands for synthetic. And synthetic because for the satellites to have good spatial resolution, the antennas need to be very large, but this is not practical. So instead, they carry a short antenna, which simulates the behavior of a larger antenna by taking a sequence of acquisitions. Now, I will start with the benefits and the advantages of this technology before we proceed with the example. So we have this technology is very economical because of its wide coverage. We have dozens of kilometers in one single analysis. Faster because it's automated, it's more accurate than visual inspection, with the technology achieving 2 to 4 millimeters. But of course, it depends on also on each analysis and also the data itself, which we always assess before each analysis. There's high frequency of data with every few days. We get new data, it's non-disruptive, it's automated. And one of the greatest advantages, I would say, is retrospective analysis. So it allows you to go back in time. We're talking about global coverage going back to 2015, where global data is available. And the importance of that is that you can detect trends of displacements early on. So by knowing the historical movements, you can see even before these are serious, before they even become visually apparent, the problems that have been developing. And in that way, you can take action. Let's see now what we measure from our SAR satellites. So we measure two main properties. We measure the amplitude of the SAR wave and the phase. So the importance of the amplitude is that if we're talking about bare ground, any changes in the amplitude would be correlated to the dielectric constant of the soil. So the amplitude would be correlated to the soil moisture measurement. But of course, the ground is never straightforward because we have vegetation coverage, we have the geological conditions, we have the slopes, we have a lot of parameters that impact this soil moisture measurement, the relationship between the amplitude. So what I will be presenting you is an algorithm we have been developing where we consider different parameters, and also this is a multi-sourced algorithm that enables the measurement of soil moisture from space. And also we have the phase difference between successive passes of our satellites. And the importance of that is that if we have a minimum of 20 such passes, then this phase difference between them can be converted into displacement measurement with millimetric accuracy. So let's start with the soil moisture. So what we can see here, this is the performance of our algorithm versus in situ soil moisture data. So you can see here, we have a very large number of data from in situ soil moisture sensors, and you can see that the performance of our algorithm against the soil moisture, it's very, very good. We have a correlation in excess of 0.8, and you can see that this correlation is particularly strong if we're talking of values up to 0.5, 0.6, which is the majority of the situation. For this, we have used data from more than 40 countries, so it's globally applied. And the reason we used all this data is so that we account for the different conditions, different characteristics. We consider the climatic conditions of each location in our data. Also, the data captured for over 3 years, and we keep adding more data. And the importance of that is that we can capture also the seasonality of the data. And we have applied it commercially in different places, in Australia, New Zealand, in Singapore, in Indonesia now. So let me show you some examples. So this is an example where we applied this in Singapore. So we are interested in monitoring the soil moisture over this area. And that's what the output looks like. So we get the soil moisture data, the pixel level. This is an image captured on 20th of February and 2023. So what you can see here, we're talking about volumetric soil moisture content up to between 5 to 10 centimeters. So it's artificial. You can see the light color here. So we have low values of soil moisture content. And if you compare, if you look at if you look at the rainfall data, which we were very lucky to have a weather station nearby, you can see that 20th of February we're here and we had very little rain the days before. That's why we have very low values. If we now move to a few days later, so let's move to 16th of March, you can see immediately the difference. So we have much darker color now. And if we look at also our weather station, the rainfall data shows that we had a lot of rain the days before. And for this reason, we had an increase in the soil moisture data. You now might be asking what's happening with comparison with in situ ground rate data. So let me show you this example here in New Zealand. So in this case, the client was interested in monitoring the soil moisture over time. So this is just an image between a dry season and a wet season. And let me show you what happens here with ground truth data. So in black, we can see the in situ data from that site. So what we can see here is clear separation between the wet and the dry season. So we have reduction of the soil moisture, increase, reduction and increase, so on and so forth between the wet and dry season, apart from 2023 where we had a lot of rain. Our model, you can see its performance in red. So this is the performance of the model without any knowledge of the in situ data. And you can see how well it performs, identifies clearly the difference between the seasons, and behaves very well. The blue one shows our model by using some of the client's in situ data, not that specific location, but other ones in the area. And of course, it's expected if you have in situ data, the model will improve and perform better, but even without, it still performs very well. Now, regarding its applications to the rail lines. So let's look at it here where we have applied it. So this is a section of the railway line. And what we can see here visually is that we recognize a white patch in this circle here. And if we look at the soil moisture values for different dates, we can see here each color line represents a different date, and we can see that in this exact location, we always get a peak. And the importance of that is that this could be an indication of poor drainage and indication of ballast fouling. Now, let's look at how we use satellite technology for displacement measurements. So how this works, we have our satellite data here, scans the Earth's surface as shown in this shaded area. So we can see the dominant target here. We have this building. So the satellite sends out electromagnetic radiation and is a blue wave. And from the building, it is reflected back to the satellite. Imagine that the second time that the satellite passes, sends out the red one, hits the building, but something happened in between, and this building has moved to this new shaded location. So it means that it will hit it at this location, and the wave will be reflected back. So what we can see is a phase shift or a phase difference between the blue and the red. And as I mentioned earlier, if we have a minimum of 20 such images, this phase difference can be converted into displacement with millimetric accuracy. Let's look at some examples of applications. So this is a video that shows the railway line is a very good scatterer, this railway corridor here. You can see clearly orange and green sections. So the green means sections with relative stability, and the red points are showing movement, increasing the displacement. So for each of these dots, you can get information about the location, lat long, about the velocity. So this one is moving with 13 millimeters per year. And in that way, you can compare it with any other location. So let's compare it with the blue one here. So it's the red and the blue. The blue is relatively stable, and you can extract the data and download them, or extract them in CSV or a format that you can work on your own. Okay, this is another great example where this is a monitoring of, this is in South Africa, a railway corridor here. And what we can see here is that we can see a difference in the behavior of these two locations, the red one, in September 2019. So this is an example of an early warning that we provided to the client. So until then, both points had very similar behavior, but something has triggered the movement of this location here. So in that way, we have provided an early warning to the client early on, and they can pay attention to the area. But not only it's important to know that you have displacements, but also provide information regarding the type of displacement. So you can have different types, and we have developed automated algorithms where you can identify points that exhibit different behavior. For example, not only the stable points, but which ones are increasing linearly or decreasing linearly, where you have acceleration in the movement, or deceleration, or seasonality, or triggering. And in that way, you can have a whole analysis which can separate the points based on the behavior they exhibit. So if you are interested in the seasonality, you can group the points based on the ones that show different behavior. Okay. And this is an example of a sleep failure. This is a well-known case in Hook that happened in January 2023. And what we can see here is increasing the movements from 2 years before in this specific location. And the results, of course, can be plotted in different ways to be meaningful. So in this example, we have a plot of the chainage. So this is along the railway line, and this is the track roughness. So what we can see here is that at this location, just after 3,000 meters, we have increase in the velocity compared to the mean velocity. So you can see that the mean velocity is around 0, but at this specific location, and of course at this, we had points with a much higher velocity compared to the mean. Of course, also we can plot that with the standard deviation, and you can see that the standard deviation is much higher at this specific location. Now this is one example. This is from a road network, but just to show you how this works. And in this case, we had, this is from UAE. This is a road between Dubai and Fujairah. So what you can see at the bottom one, this is a 70-meter earth retaining structure. So we can see that this is a reinforced soil wall, and we can see that over a 4-year period, it had near 0 vertical displacement, supporting the highway very well. And a few, I think 500 meters away, this part of the highway is supported by an embankment, and we have some increasing displacements at this location. And this is another example. This is for the embankment. Here, this is a project in Glasgow. It's a Rob Royston. So the reason I'm presenting this is because it's a very interesting case of very variable geological conditions here. There was in situ monitoring, which at some point it stopped functioning properly. And we provided updated monitoring every few months for this one, as well as a finite element analysis. And we compare it at the end, as I will show you. So what we did, we divided this into 4 sections, this embankment. And let me show you some examples. So we're talking about the vertical displacement here. So between September 2021 and March 2022, so over a 6-month period, we had displacements up to 15 millimeters. So if we're talking about the rate of movement, this is up to about 30 millimeters per year. The next section, section C, we had somehow increased movement. So this one reached up to, let's say, 25 millimeters in 6 months. So that's 50 millimeters per year. And for section D, about the same, 15 millimeters in 6 months, that's 30 millimeters per year. And at this slide here, I'm showing you the results from the finite element analysis. So what we can see, we have two scenarios here for different geological conditions. So the first one is the good scenario and the bad scenario. So we expect the maximum post-construction settlement at the beginning, the first few years upon construction, and we can see that the values vary between the rates, vary between 30 millimeters per year and 100 millimeters per year. And what we can see is that we predicted that, but with actual monitoring updated every 4 months, every few months, we had values between 30 and 50 millimeters. So that was well within the, let's say, the expected values. So that provided confidence, of course, that not only they predicted that, but also measured the actual displacements. And this is road network monitoring. So this was a very complicated project, and the reason I'm showing is that we had to deal with flooding and snow in the area. So we had to exclude a lot of images due to this disturbing data due to the flooding and the snow, but we still got a very good results. So this is a project from a place called Taylor near Austin, Texas. So the important thing here was to identify the part of the road network that was suffering from expansive clays, as well as the magnitude. So you can see here clearly that the green areas are areas that are relatively stable, but the yellow and orange are areas with increased movements. And if we look at some of the results, what we can see here is that we have 3 points. So we have the red one, this is a blue circle, and the green. They are very close together, but we can see that these two, they have strong seasonality in the data. So you can see peaks in around May every year. And when you compare this with the precipitation data, this is in good agreement. So the maximum rainfall occurs in about April, May in this area. And the green point shows relative stability because we're talking about a much more, let's say, a much bigger road here. So these are neighboring roads. This is a much bigger road with much stronger foundations. And now I will talk about infrastructure susceptibility to geohazards. Okay, so we talked about displacement data. We talked about soil moisture data. We also incorporate in our models, in our algorithms, other important information for the different geohazards. For example, the slope, also the aspect, let's say the presence of vegetation, the geological maps. The geology is very important. Asset damage data, ground truth data. So a lot of information incorporated into the models using AI. And we do that for assessing susceptibility to geohazards such as landslides, expansive clays, and sinkholes. And I will start with a video. So this what I wanted to show you here, what the outputs look like. So this is a map which shows you categorization of the susceptibility. We have the red one shows high susceptibility, the orange shows moderate susceptibility, low and no susceptibility. So you can overlay this map over your entire network, and in that way you can identify which areas are susceptible to these geohazards. And the importance of that is that these maps can be updated frequently. So, of course, you can get landslide inventories published by geological surveys. With this method, we can update the maps very frequently, let's say at the end of every raining season, to capture the triggering of new landslides, for example. While the landslide inventories, especially at country level, because of the amount of work, it's very time-consuming process, and it takes years for updating this information. And this is a map. We did this for California, so for the whole of California, and you can see the differentiation in the categorization, and you can get that at a very good pixel size resolution. So at about 10 meter by 10 meter pixel size, you can get the differentiation between the different categories. And here I wanted to show you some of the results. So this is again the California landslide susceptibility map. We also provide here the part of the rail network that passes through this landslide susceptibility map. And I wanted to show you some of the results in 4 areas. So you can see that parts of the rail network, they go through some areas of moderate susceptibility in these locations. So in that way, as I say, is while in this section you have no susceptibility, it means that you can proactively do something about this and also provide more assessment at the specific locations and be more efficient with your resources. And this is the second area. So the second area, again, we have several areas. You can see that the whole network goes through different susceptibility scores. Again, this one as well. Areas with varying from no susceptibility to moderate susceptibility, which is the orange color. And also some of the actual INSAR outputs. So here you can see, indeed, we have some increased displacements and here as well some movements. What I wanted to point out here is that you have full coverage with known gaps in the data. And the reason is because of the great number of data and the correlation we develop between the different parameters. We're able to fill even the gaps between the outputs, even when you don't have high density of points. And we have also done similar work for the expansive clays. So again, in the models, we account for different parameters that are important for the susceptibility to expansive clay. So what I'm showing here is a map that shows the severity score to building or infrastructure damage. And in the map, in the geological map, this layer here is shows as the same type of clay. But what we have done here, we categorized it into different severity score. So there is a different score to causing infrastructure damage. And to prove it, let's look at this very light color. We have the lowest severity score. And if we look at the actual movements, we can see that there is no displacement in this location. The darker color shows higher severity score. So we're now in the darker color, and we have, the reason is because we have seasonality in the data. And if we look at the even darker color, we have higher severity score because we have both seasonality and downward movement. And as I mentioned earlier, this is not just the output of the displacement, It's the output of the multi-source data, where we use also the soil moisture information in this map, as well as other information, topographical and geological. And that shows the correlation between the soil moisture and the displacement. So for every location, we are able to measure both the soil moisture and the displacement, and determine this correlation, which is not always the same because it depends on different factors. So what we can see here is that we have the volumetric soil moisture content in black. The axis is here. So you can see the difference between dry season, wet season, dry season, wet season, and how the displacement reacts. So we can see that the displacement follows in this specific case, but we can do that for each specific point. And to conclude, we have seen that soil moisture data by satellite can provide global coverage and is updated with every satellite pass. Also, we saw how we can use displacement monitoring for geotechnical infrastructure assets, and how these can be correlated with both in situ instrumentation and finite element analysis, and also how we use multi-source data in machine learning and with AI for susceptibility to geohazards, and how this can be used for climate change, because they can easily be updated to incorporate, let's say, any changes. So we can update them with every rainfall event and at the end of every raining season. And that's very good for reduction of carbon footprint. And how having information about the soil moisture and displacement is very important for assessing the condition of infrastructure assets. That's it from me. Thank you very much, and I look forward to a discussion and any questions you may have.
Excellent. Thank you very much for that. That was really interesting. There's one question currently in the chat. So Gavin asks, how effective is the technology on non-reflective surfaces? For example, the difference between rural and urban. Is there any difference, or does it not matter?
Very good question. Of course, yes, good question, because there is difference. Depending on the type of surface you have, you select different bands. So if we have rural areas or vegetated areas, let's say, we have less penetration, so we need to use a different band. Most of the examples I showed are with the open source Sentinel data, the ones I showed here. We have examples with other satellites. So if you have vegetation, you will either use, depending on the density of vegetation, different technique like distributed scatterers, which allow to get more data than the persistent scatterers, but you may also use, let's say, L-band data.
Okay. Interesting.
So it is important. Thank you. Yes.
Yeah. Have you got any experience with behaviors of peat?
Sorry, what is the question?
So do you have any experience with modeling the behaviors of peat? So as a subgrade soil, yeah. Okay,
the modeling in finite element or in working with peat in displacement, we use in our geotechnical models. Yes, in working with displacements. If you give me some more information, I can expand a bit more. Yes.
Right. So peat is. Do you know? I mean, peat is a very soft.
Oh no, I know what.
Yeah.
Yes. So, I don't know whether it's in terms of displacement monitoring or in terms of geotechnical.
Right. Yeah, it was my question. I was wondering about displacement monitoring.
Yeah, yes, and in a lot of in a lot of the projects we do, yes, because it's a surficial displacement we're monitoring, and a lot of the times we have peat. So yes, we do have experience in that. We have some examples. If you want to send me an email, I can send you some case studies or present some examples on that.
That's great. Thank you.
Thank you.
Yeah, very interesting. So in terms of the soil moisture content, how deep does that measure down into? Because I'm just thinking that example you showed of the wet bed, that would obviously be a case of there's water underneath the track that's causing the subgrade to pump up into the ballast. So what sort of depth does it is it measuring into?
Mm-hmm. Yes, this is surficial, so it's 5 to 10 centimeters.
Right. Okay. So it's okay. So I'm just thinking in terms of ballast. So if we were trying to determine if there was more water within our track bed area, it's sort of only the top sort of layer that we're seeing that, almost
Yes,
like
yes,
runoff content,
yes, yes.
perhaps, that kind of thing. Right.
Yes,
Okay.
what we do in a lot of the times, because we compare this spatially, so with the neighboring pixels, and also over time, you can detect differences in the behavior, let's say, between that specific pixel with others over time. But yes, you are right. This is a 5 to 10 centimeters is sufficient.
5 to 10 centimeters, right. Okay. Somebody's asked a bit of a technical question, I guess. How do you manage instrument degradation and orbital decay when calibrating your instruments?
Okay. This is satellite data. So what we provide is the processing of the data. So if there is any, and we also allow for orbital corrections in our data. So if there is a problem with the satellite, so we don't calibrate the instrumentation. We're talking about in situ instrumentation. We provide analysis and comparison with our data. So a lot of the times we have examples of settlement plate tests, inclinometers, and GNSS data, so you can do that. But yes, orbital decay, this is a responsibility of the satellite providers, but we only account for this information.
Right, and I guess do they alert when something's gone wrong so that you can ignore data, that kind of thing? So
yes, maybe I didn't understand also the question. If there is also, of course, we know exactly what's happening, but also whenever there is either some problems, not problems, we can remove, let's say, images with sometimes, because atmospheric impacts are very important, even though we correct. If there are some issues with the satellite itself, we will remove it or provide some corrections, definitely.
Yeah. Okay. So is this mapping happening all the time then, or do you only cover areas that you are specifically engaged with, or is it the data that you've got constantly being churned away for everywhere? Just curious.
I wish we, yeah. At the moment we do that per project basis, so we don't have global coverage. And there, okay, we have analysis for very large areas. I mean, I showed you the example of. Let's say California, we have done it for large areas in New Zealand, and we are also updating this information, but it's not globally available.
Right.
Yes.
Okay.
We do it on demand.
Right. Okay. So we've got another question. So when concerned about a geohazard, how often have you modelled an area? Is there any standards? So I guess they're asking, when you get asked to look at somewhere, what sort of frequency and how often do you go back, I guess, is the question.
Yes, I think this depends on the needs from the client. So we have done it for every quarter, we have done it for every year so far. Depending on the needs, there are no standards. But I can see it's very, very important, especially due to climate change and all these unpredicted weather sometimes. So you can see, as I said, it's very important, especially for the triggering of new landslides. At the moment, I would say every quarter or every 6 months, most of the clients are asking for. And if anybody is interested, we have recently published in 2 journals the geohazard susceptibility mapping, and I'll be happy to share it.
Okay, yeah. Yeah, that would be interesting if you could somehow. Yeah, we'll try and dispense that. If anybody's interested, we'll pass on that information.
Yes,
I guess because I'm kind of thinking from in terms of network rails infrastructure, different disciplines would need the information at different times. So it's interesting when you say, how often you go back, and you tend to be like a 6-month basis. So from a track point of view, we very often measure. We have our recording runs done every 4 weeks. Hopefully, not always. Whereas I guess earthworks, who would be interested in some of the stuff you were talking about in terms of displacement of earthworks and embankments and things, I guess they might be on a longer timescale. I'm not sure. I'm not fully au fait with with geotechnical that side of things, the asset management. But it would be interesting to see how we could use that information, like say, certainly from a track point of view, whether it would be quick enough, because I guess once a month might be a bit excessive from your point of view in terms of how much data you'd be trying to digest and churn out, I guess, because we'd be looking for the whole network. If Network Rail was going to do something like this, it would be everywhere. So that's a lot of data, isn't it? So that might be a big ask, I guess. No, that's interesting. So if there's no other questions, then if we could just show our appreciation in the usual manner, that would be brilliant. Thank you. I don't know how we do that these days. I don't know if you want to take yourself off mic and applaud or something. I don't know. Just wave your hands, whatever it is you do. Oh, that's great. Thank you very much for giving that presentation. That's really